Hey guys, you're welcome once more to this YouTube channel. Today we're looking at solutions to NABTEB GCE 2023 Chemistry Examination, NABTEB November 23 GCE Chemistry Main Paper. So stay with us as we roll through these questions. If you're not subscribed or you're seeing this channel for the very first time, please try as much to subscribe to the channel. How do you subscribe? Move up to the top of the channel, you see the profile picture. At the profile picture, you see the name of the channel, Best Science Brain. Then under the name of the channel, Best Science Brain, you see subscription with a button. The button looks like a tiny bell. Close to subscription, tap on subscription or tap on the button and get subscribed to the channel. Tap only once and get subscribed. So why do you get subscribed? So that whenever we post our videos on solution to examinations or on tutorials on chemistry, further mathematics and physics, you'll be among the first to get our video notifications. So just a little sacrifice and then you will enjoy. Then if you're writing WAEC, NECO, JAMB, you are in A-level, first CS Conye of the high institution, this YouTube channel is for you. So subscribe if you are not subscribed. Thumbs up for those who are subscribed. For our subscribers who have been following the channel, we appreciate you all and we promise to be giving you the best. So we'll move to chemistry main paper questions, November 23, NABTEB GCE. NABTEB GCE. So let's go to number question 1A. It says define oxidation and reduction in terms of electron transfer. Define oxidation and reduction in terms of electron transfer. Solution: oxidation is the loss of electrons, reduction is the gain of electrons. Oxidation is the loss of electrons, reduction is the gain of electrons. 1A. Define each of the following terms. A. Electrolyte. B. Non-electrolyte. C. Conductor. Solution: electrolyte is a substance which conducts electricity only in aqueous or molten state by movement of ions, and it is decomposed in the process. B. Non-electrolyte is a substance which does not conduct electricity in aqueous, molten, or liquid state due to the absence of mobile ions. I repeat, non-electrolyte is a substance which does not conduct electricity in aqueous, molten, or liquid state due to the absence of mobile ions. Then C, conductor is a substance which conducts electricity by movement of the localized valence electrons. Then 1A. State one example of each of the terms listed in 1A above. So we have to give example of electrolyte, non-electrolyte, and conductor. Solution: electrolyte example is aqueous sodium chloride. So the word aqueous must be mentioned. You don't mention only sodium chloride. Either you say aqueous sodium chloride or you say sodium chloride solution. Because other examples could include potassium chloride solution or aqueous potassium chloride. Another example can also be hydrochloric acid solution, tetrasulfuric acid solution, sodium triiodide solution, sodium hydroxide solution, potassium hydroxide solution. All these electrolytes. The non-electrolyte, an example is benzene. Other examples may include tetrachloromethane, trichloromethane, ethanol, kerosene, petrol. All these are non-electrolytes. Then conductor, example here is copper. Other examples could be any metal like zinc, aluminium, Any metal you can never remember: sodium, calcium. Metals are conductors. You can as well mention graphite, which is the only non-metal that conducts electricity. Going to 1B, says state two chemical tests for reducing agents. Solution number 1, we asked to state two chemical tests for reducing agents. Okay, let's go to solution number 1. The first test: when a reducing agent is passed into a solution of acidified KMNO4 aqueous. KMNO4 means potassium tetraoxomanganate 7 solution, the color of the solution changes from purple underlined, to colorless also underlined. The second test: when a reducing agent is passed into a solution of acidified K2CR2O7, which means potassium heptaoxodichromate 6 solution. The color of the solution changes from orange to green. So in both cases, note that the chemicals must be acidified KMNO4 and acidified K2CR2O7. And also note the color changes: the color before passing the reducing agent and the color after passing the reducing agent. This one is purple to colorless, must be mentioned, and this one orange to green must also be mentioned. We go to 1CI that says a 5.0 grams of magnesium hydroxide neutralizes 450 cn³ HCl, full stop. What the concentration in mole per dn³ of HCl in the solution? A 5.0 grams tablet of magnesium hydroxide neutralizes 450 cn³ HCl, full stop. What is the concentration in mole per dn³ of HCl in the solution? So let's go to the solution. The first thing you have to do is to write the balance equation between magnesium hydroxide and HCl. The equation goes thus: 1 mole of magnesium hydroxide plus 2 moles of HCl gives us 1 mole of magnesium chloride plus 2 moles of water. Then we'll calculate the molar mass, that's mm, of magnesium hydroxide. The atomic mass of magnesium is 24 plus, bracket opens, atomic mass of oxygen is 16, and had is 1 added in the bracket closes, you have 2. That is called 2 you have there. Then multiply by 2, solving out, you have 24 plus 17, summing out the bracket, 17 times 2, that is 34. Then adding 24 and 34, you have 58 grams per mole with the unit of molar mass. Then you find the mole of magnesium hydroxide. The reacting mole of magnesium hydroxide is given by mass over molar mass, that is m over mm. We're going to be 5 over 58. The mass is 5 grams, as given in the equation. 5 over 58, where 58 is the molar mass. Then that will give us, divide 0.0862 mole of magnesium hydroxide is reacting. So that's the reacting mole of magnesium hydroxide. We'll now go to the stoichiometry. For the balance equation, you can see the balance equation. 1 mole of MgOH is balanced by 2 moles of HCl. So 1 mole of MgOH bracket 2, that is magnesium hydroxide, equivalent to 2 moles of HCl. Therefore, 0.086 mole, which is the reacting mole of magnesium hydroxide, mole of MgOH2, will give us 0.0862 times 2. That will give us 0.172 mole of HCl. So 0.172 mole is the number of moles of HCl that will react with 0.0862 mole of magnesium hydroxide. So applying the formula, mole equal to CV over 1000. That is concentration in mole per dnq. V is volume, which is the 450 into in the equation. The 1000 is used to convert that volume in cn cube to dn cube. So making C the subject, C becomes n times 1000 over V. Then that gives us 0.172 times 1000 over 450 after doing proper substitution. Then our C or Ca is going to be 0.382 mole per dn cube of the acid. Going to 1C double I. List 4 factors that affect the rate of chemical reaction. Solution. Number one, the one is temperature of reaction system. You have to mention reaction system. Don't just mention temperature. Temperature of reaction system. Presence of a catalyst. You don't just say catalyst. Presence of a catalyst. Then concentration of reactants. You don't just write ordinary concentration. Concentration of reactants. Or you can say pressure of gases. Pressure of gases. The two are tied. So you don't separate them. Either you write one of them. Don't write them as separate factors. Then surface area of reactants. You don't just say surface area. Surface area of what? That equation. Surface area of reactants. Temperature of what? Temperature of the reaction system. Then concentration of what? Concentration of reactants. Pressure of what? Pressure of gases or pressure of gaseous reactants. So these are the factors that affect rate of chemical reaction. The other factor like nature of reactants can also be and that factor affecting rate of chemical reaction. Then going to 1D that says state 3 uses of electrolysis. Number 1, extraction of highly electropositive metals such as sodium, calcium, and aluminium from their ores. So you must give examples of such metals. So don't just say extraction of metals and stop there. Extraction of highly electropositive metals such as sodium, calcium, aluminium from their ores. Number 2, replating of metals such as silver plating of a steel rod. Yes, silver plating of a steel rod, gold plating of a steel rod, and so on. The number 3 example is number 3 application or use of it is a purification of impure metals. Impure metals such as crude or impure copper. Purification of impure metals such as crude or impure copper. So the other uses. So these are 3 basic uses of electrolysis as we are asked to provide. Going to number 2, 2A says list the products at the anode and cathode of electrolysis of aqueous sodium hydroxide using platinum electrodes. The products at the anode and cathode of the electrolysis of aqueous sodium hydroxide using platinum electrode. So solution, the product at the anode is oxygen, at the cathode is hydrogen. Anode, oxygen gas is liberated, at the cathode, hydrogen gas is liberated. 2B says, explain the following bonds and give one example in each case. I, DT bond, II metallic bond, III hydrogen bond, IV ionic bond. So we're going to explain this. That means this requires short note each. And in each case, we give one example. Solution, DT bond. So go there. This is the type of bond which occurs when both electrons shared in a covalent bond come from one of the atoms. Full stop. One atom donates the lone pair of electrons to the bond, comma, while the other atom does not contribute any. Full stop. This creates a special type of covalent bond where the shared electron pair comes from the same atom, comma, forming a bond with a distinctive directionality. So you can see it. Okay. A typical example of is the formation of ammonium ion, bracket NH4, then positive charge, bracket closes, comma, where the nitrogen atom shares a lone pair of electron with the proton. So you can see the schematic illustration. You can see ammonia with its trigonal pyramidal shape, ammonia, and they have the lone pair of electron, those two dots on top of nitrogen, combined with hydrogen ion, which is also referred as a proton. The hydrogen ion has no electron on it, and for hydrogen ion to has no electron in the case shell, 0 electron. For it to attain duplex state, it has to gain 2 electrons. So that 2 electrons is going to share with the 2 electrons from nitrogen in ammonia. So when they come together, you now have a kind of tetrahedral shape. You can see the bond occurring there between the upper hydrogen and then the nitrogen. So that is the T bonding. And the charge on the proton is now shared, delocalized, is now shared by the whole atoms NH4. That is dative covalent bond, dative bonding, otherwise known as coordinate covalent bonding. So 2BII metallic bond. Metallic bonding is a type of bonding found in metals where electrons are delocalized and move freely throughout the structure. Metal atoms collectively share their electrons, creating a sea, creating a, have inverted comma opens, sea of electrons, inverted comma closes, that holds the metal cations together, full stop. Metallic bond arises due to the electrostatic force of attraction, should be force of attraction, of is missing there, force of attraction existing between the positively charged metallic nuclei and the sea of valence electrons, in bracket electron cloud, bracket closes. So that is the description of metallic bond. We'll go again. Using copper as an example, each copper atom donates one or more electrons to the electron sea, forming a structure whose electrons are not fixed to individual atoms, but instead move throughout the metal lattice. So that is it. So we'll go to hydrogen bonding, 2B-triple-I. Hydrogen bond is an intermolecular attractive interaction. You can still call it an intermolecular attractive force. Now the word intermolecular must be there. It's not intra, but intermolecular, between one molecule and the other. So say hydrogen bond is an intermolecular attractive interaction or force between hydrogen atom covalently bonded to a highly electronegative atom such as nitrogen, oxygen, or fluorine. Full stop. An example of hydrogen bond is observed in water. Hydrogen atoms are covalently bonded to the oxygen atom. Full stop. The highly electronegative oxygen attracts the electrons more strongly, creating a partial negative charge near the oxygen and a partial positive charge near the hydrogen atoms. Full stop. This sets up hydrogen bonding between water molecules. So we can see the schematic illustration, water molecule joining to each other. So the intermolecular force between one water molecule and the next is hydrogen bonding. You can see, look at the first molecule, you can see the central oxygen bonded to hydrogen, and you see the dotted line. That dotted line represents a covalent bond shared between hydrogen and oxygen. And a covalent bond indicates two electrons shared or a pair of electrons shared. Now, why is that bond broken? It's because there's a kind of tug of war on who is superior than the other between hydrogen and oxygen, who is going to attract electron. There's a fight between the two of them. So the oxygen atom tends to pull the electron more than the hydrogen because oxygen is more electronegative than hydrogen. But would oxygen take the whole electron and leave hydrogen empty? No. Hydrogen will still partake in the sharing, but with electron being pulled closer to oxygen than hydrogen, that gives oxygen partial. That letter looks like delta or small d is called partial. Oxygen partial negative charge on both sides and give hydrogen partial positive charge. So you can see the illustration of hydrogen bonding. Two CI says, for how long does a current of 1.0 ampere need to pass through a solution of CuSO4 to deposit 2.2 gram of copper, in bracket, copper atomic mass is 64, 1 Faraday is 96,500 coulombs. I repeat, for how long does the current of 1.0 ampere need to pass through a solution of CuSO4 copper 2 6 to deposit 2.2 gram of copper, and in bracket we're given the atomic mass of copper and the Faraday constant. Solution, the first we have to write the equation on the cathode reduction of copper 2 ion to ordinary copper. You can see 1 mole copper 2 ion in aqueous state plus 2 moles of electron, giving us 1 mole of copper in solid state. Then going from the balance equation or from the stoichiometric reaction, we have 1 mole of copper being equivalent to 2 moles of electrons. So 1 mole of copper equivalent to 2 moles of electrons, and 1 mole of copper is sent as the atomic mass given to us in bracket. So 1 mole of copper replaced by 64 grams of copper equal to 2 Faraday, because 1 Faraday is equivalent to 1 mole of electron. We'll come again to 4 grams of copper equal to 2 times Faraday constant is 96500 coulombs, replacing F with 96500. Then open the bracket, will come again and says 4 grams of copper equal to 193,000 coulombs. Therefore, 2.2 gram given the equation of copper will now give us 2.2 times 193,000 all over 64, and that will give us 6634.4 coulombs of electricity. That's the quantity that was passed during the experiment actually. Then going from the formula, Q is equal to IT. We make time the subject, time becomes Q over I, and then Q is our 6634.4 over I is the current. The current is 1 ampere all over 1. So we'll divide, we'll still have the same 6634.4, but this time around in seconds as our answer. Okay, can view it again. So how to see II says three differences between liquids and solids. Three differences between liquids and solids. So there are many differences which to itemize on the table. You choose three. Solution, we have a table drawn there. Solids, liquids and solids. Liquid on the left hand side, solid on the right column. So number one, liquids do not have definite shapes. Full stop. They take the shape of their containers or their vessels. Number one, under solids, solids have definite shapes, maintaining a fixed and rigid, R-I-G-I-D, and rigid structure. Number two, liquids have a relatively lower density than solids. Liquids have a relatively lower density than solids. Number two, solids have a higher density than liquids of comparable volumes. Number three, molecules of a liquid are disordered, allowing them to flow past each other. Molecules of a liquid are disordered, allowing them to flow past each other. That should be pass, should be PASS, please. Correction. Then number three, Particles or atoms in solids are closely packed in an ordered repeating pattern. Number 4. Liquids are characterized by moderate intermolecular forces such as van der Waals forces, van der Waals, W-A-W-W-A-L-S, but it's pronounced as Waals because it's a German word, not Waals. Van der Waals forces, dipole-dipole interaction, and hydrogen bonding. In studies, number 4, studies have stronger intermolecular forces leading to a more ordered and structured arrangement, full stop. These forces include ionic, covalent, metallic, and sometimes hydrogen bonding. The other differences between solids and liquids anyway. So we need only three points here. Difference between solid and liquid, need only 3 points. So you can still have other ones that are correct. 2C triple I. Say, what is the mole of a substance? Solution. A mole is defined as the amount of substance which contains as many elementary particles, atoms, molecules, or ions in bracket as there are carbon atoms present in 12 grams of carbon-12 isotope. So that is the mole for you. Then number 3AI says, what is the strength of an acid? Solution. This is the ability of an acid to donate protons, or you can say hydrogen ions, in aqueous solutions. Full stop. Strong acids ionize completely in aqueous solutions, while weak acids ionize partially in aqueous solutions. Then 3A says, state Avogadro's law. Solution. Avogadro's law states that quotation quote, equal volumes of gases contain the same number of molecules at constant temperature and pressure, unquote. Equal volumes of gases contain the same number of molecules at constant temperature and pressure. That's Avogadro's law. Then 3A says, what is Avogadro's constant? Solution is the number of entities, E-N-T-I-T-I-E-S, bracket opens, atoms or molecules, bracket closes, present in 1 mole of a substance, full stop. It is approximately equal to 6.02 times 10 to the power 23 particles. So yeah, as for the Avogadro's constant, you have to first of all define Avogadro's constant as I define it here. And then before you give the value, you don't just give the value as 6.02 to the power 23 and walk away. No, it doesn't work like that. 3B. The electronic configuration of elements C and D are 286 and 282 respectively. Full stop. Number 1. Name the elements C and D. Let's go straight to the solution. C is sulfur, based on the fact that the electronic configuration is 286. 286, you add the electrons, 2 plus 8 plus, it gives you 16. The element whose atomic number is 16 is sulfur, that's why C is sulfur. And then D is magnesium. Why? That if you look at the electronic configuration 282, add the electrons, 2 plus 8 plus to give you 12. The element whose atomic number is 12 is magnesium. So we'll go to number 2 question. Number 2 says, write the formula of the compound formed when the two react. That's when the two elements react. So going to number 2, formula of compound will be DC. D will come before C because D is a metal and C is a non-metal. The valency of magnesium is 2, and the valency of sulfur in binary compound is also 2. So the 2 cancel, you have DC. Or you can still use the formula MgS because the names have already been mentioned. Mg is for magnesium, that is D, and C for sulfur. Then triple I says, question I give the properties of the compound formed. That the compound formed with this number 2. The compound properties are high melting point and boiling point. And then number 2 is a solid consisting of aggregate of ions. Number 3, soluble in water or polar. Then number 4, Aqueous solutions of that compound conduct electricity, or the aqueous solution is an electrolyte. So these are the properties any two can score. These are the properties of this compound, DC or magnesium sulfide, based on the fact that it's an ionic compound. So the properties should be properties of ionic compound. Going to number 4, says what type of bonding is involved in BII above. What is BII? It says write the formula of compound form. Okay, the kind of bonding involved in this formation of a DC. So the answer, as we said before, ionic or trivalent bond, because it involves a metal and a non-metal. So go to number 3C. It says using a well-labeled diagram, describe the preparation of dry ammonia. Give the equation for the reaction. So there are about 3 questions here. We're going to draw a diagram for preparing ammonia. We're going to describe the preparation briefly, and then we're going to also write the equation here in this 3CI. Start with the description. Ammonia is prepared in the laboratory by heating a mixture of slaked lime in bracket Ca bracket opens OH bracket 2. Slaked lime is also calcium hydroxide, and ammonium chloride, full stop. The issuing gas is dried by passing it through a drying tower containing quicklime. Quicklime in bracket is CaO, that is calcium oxide, and collected by upward delivery. So the equation is given to us there. 1 molecule or 1 mole of calcium hydroxide plus 2 moles of ammonium chloride. The arrow is drawn, and under the arrow write heat. Then product 1 molecule of calcium chloride plus 2 moles of ammonia plus 2 moles of water. Going to the diagram for preparation of ammonia, you can see everything. You have a hard glass boiling tube, HARD, hard glass boiling tube, labeled there, and make sure that in your labeling the arrow should be pointing directly on what you want to label. Look at that arrow pointing on hard glass. It's touching the glass, not inside the glass. Then look at the other one, the reactant, calcium hydroxide and ammonium chloride. The arrow is pointing inside the substances that are shaded inside. Then heat under it. Then we have a retor stand holding the hard glass tube, and then the hard glass tube is in a slanting position, sloping downward. It should not be horizontal, sloping downward. Look at the shape of the hard glass tube. They have the delivery tube, and then we have the drying tower labeled, pointing on the tower. We have the quicklime or calcium, the substance that are inside the drying tower. They have the glass going up there. The dry ammonia, and then the gas cylinder. The gas cylinder, look at it, is covered under, so that gas will not escape. And the delivery tube pointing inside, going inside the gas cylinder. So you can see. So this is the preparation of dry ammonia. So you can see, consult a good textbook and say, look at it again. And then when you are drawing your diagram, you make sure that the retor stand and the drying tower are on the same base. You can see the line drawn on the base to show that they are starting at the same level. None is hanging in air. So you have to make your diagram workable. And you draw very well and label very well. Okay, now going to 3CII says, state 3 postulates of the kinetic theory of gases. 3 postulates of the kinetic theory of gases. Solution. Number 1, the volume occupied by a gas molecule is negligible, meaning very small, compared to the total volume of the gas vessel. The volume occupied by a gas molecule is negligible or small compared to the total volume of the gas vessel. Number 2, collisions between gas particles or gas molecules and between molecules and the container walls are perfectly elastic. Collision between gas particles or molecules and between molecules and the container walls are perfectly elastic. Number 3, gas molecules are in continuous random motion. Gas molecules are in continuous random motion. So these are the assumptions of the kinetic of matter. The other statement, we will have to choose 3 here. Number 3D says outline the general principles for the extraction of zinc. So let's go to solution. We'll have number 1, roasting in air. Roasting in air, that's the first step involved there. The zinc ore, otherwise known as zinc blend, BLENDE in bracket, is roasted in the presence of oxygen to give zinc oxide. The equation goes 2 moles of zinc sulfide plus 3 moles of oxygen, giving us 2 moles of zinc oxide, 2ZnO2 plus 3 moles of sulfur oxide, SO2. That's the equation. Then the next step, reduction of zinc oxide. Reduction of zinc oxide. Then you read the zinc oxide is then mixed with coke and heated in a furnace, where it's reduced to metallic zinc. The equation goes ZnO plus C, that's zinc oxide plus carbon or coke, giving us zinc plus CO, or 2 moles of zinc oxide plus C gives us 2 moles of zinc plus CO2. The equation is correct. Then collection of zinc. Collection of zinc, that the next step involved in zinc extraction. It reads zinc's vapor is collected and condensed to metallic zinc. Full stop. Pure zinc can be obtained by electrowinning. In this process, the zinc obtained in the above process is dissolved in H2SO4 to produce zinc 2 solution, that is ZnSO4 solution. Full stop. The zinc 2 solution is subjected to electrolysis using zinc electrodes. Okay, so that is what you need, or the process involved in zinc extraction. Describe fully with the equations involved. In question 2b, we are to explain the following bonds and give one example in each case. We have answered this question before, but there was omission. We have answered dative bonding, metallic bonding, hydrogen bonding, we omitted ionic bonding. So we're going to do that of ionic bond now. So here we go. Ionic bond 2b IV. Ionic bond occurs when electrons are transferred from one atom to another, resulting in the formation of positively charged ions, bracket opens, cations, bracket closes, and negatively charged ions, bracket opens, anions, bracket closes. Full stop. The metal loses its valence electrons to form cations, while the non-metal accepts to form anions. And in the process, both ions attain stability, in bracket opens, altered state, bracket closes, full stop. The electrostatic attraction between these opposite charges holds the ions together in a stable compound. Full stop. An example of a compound with ionic bond is sodium chloride, bracket NaCl, bracket closes, full stop. Sodium atom donates its valence electron to chlorine atom such that both form sodium ion, Na, positive charge, and chloride ion, Cl, negative charge. So this is the description of ionic bonding as we have read out. Then let's go to the schematic illustration. We'll look at sodium. We'll try to illustrate using the Lewis electron dot method. Look at sodium. Electron configuration is 281. 2 in the K shell, 8 in the L shell, and 1 in the M shell. Then since bonding occur in the outermost shell, so we have to represent that dot they are close to sodium by the right, represent the electron in the M shell, which is the one electron you're seeing there. Then going to chlorine, the electron configuration is 287, right from 17. And they will have to represent the electron in the outermost or the valence electron, that is 7, since, as we said, bonding occur in the outermost electron. So we have to use, since we use dot for sodium, we'll try to use asterisk for chlorine. 7 electrons, putting the 1 along the 4 cardinal points, 1 on the north, 1 on the south, 1 on the west, and 1 on the east. After I now start doubling them. So after doubling them, we now have 2, 4, 6, 7 electrons in the outermost shell. Then, having done that, sodium being a metal will donate its 1 electron to chlorine, which is a non-metal. So in the process, when sodium donates to chlorine, the M shell sodium will become empty. That's 1 will now vanish. What will now remain at the outermost shell will now be the L shell. That is the 8 electron will now be the one we're going to have outside, as you can see there. So after the 1 electron has been removed, remains 8. Then you have 2, 8. Will now represent the 8 electrons, which is, you have it around sodium 2, 4, 6, 8 using dots. And then sodium becomes positive charge. While chlorine that access 1 will now have extra 1 to its M shell. So extra 1 to that single electron there will now be doubled, as you can see there. You can see chlorine is now complete. It's all 287 now 288. So you count the electron around it, 2, 4, 6, 8. The electron by chlorine left side of chlorine atom, or you have 2 electrons there, and one of them is dotted. That means it came from chlorine. And the day chlorine becomes negative charge, and so it becomes positive charge. Chlorine is 2, 8, looking like 2, 8. That is the electron coefficient of neon, 10 electrons, a noble gas. While chlorine is 288, the electron coefficient of argon, 18, also another noble gas. So we have come to the end of this first part of the solution. That is NABTEB GCE November 2023 GCE. Remain connected, as we're going to post the second part of the solution of this theory. No, it's not yet over. There are more other questions following of this theory to this YouTube channel. If you're not subscribed, or if you're coming across the channel for the very first time, tap on the subscription button and get subscribed for more videos. If you are a student, WAEC student, JAMB, NECO, NABTEB, whatever you're writing, or you're in A level for lectures in chemistry, physics, and further mathematics, and for tutorial, you have to subscribe and study online, study from a distance, and know it very well, and be an authority in these subjects. So remain connected, and we wish you the best.